Okay, our next topic is going to be first order logic. But first, why would we bother? I mean, we've done now propositional logic and it seems to work quite fine. So why would we want to give up on propositional logic and do something else instead? Well, yeah, let's start then with motivation. And the point here is that the propositional logic is actually very limited. To give you an example, let's look at this one. There is three statements here. The first one is every student attends lectures. Then John is a student. And from these two, I should be able to infer that John attends the lectures. And John attends the lectures should be the logical consequence of every student attends lectures and John is a student. I guess you would agree with me. But the problem here is we can't even begin to formalize this in the language of propositional logic. And why is this the case? Well, what can I do here with the first statement here? If I'd like to express it in propositional logic, I can just use a propositional variable. Let's call it P. And P can be either true or false. And then I'll have to do the same for the second statement. Let's use Q for that one. And then the third statement is going to be an R, for example. And the issue here is there is no relation between P, Q, and R. There's no way I can combine P and Q to get R without some additional formulas, but there is none, right? So there is no relation between these two formulas. And the reason why I wasn't able to do anything with them is that they are too coarse-grained. They don't go into the details of the statements here. The statement is about student and lectures and the relation between these two. And it's actually more specific. It's talking about every student, quite categorical. And then there is another student here, and it says that John is a member of this group. And then finally, again, lectures, and John is in the relation of attending the lectures. So it seems that there is a need for me to express objects and relations between them. And that's something the propositional logic cannot do. Propositional logic only deals with facts that are either true or false. And I need relations and I need objects. And that's the main motivation now for going to a more expressive system of first order logic. Another example, the Wampus world, which we talked about at the very beginning. You recall that the problem here, an example problem, is to have an agent here that needs to find the gold. There's the monster Wampus here that emits stench. There is pits in this virtual world as well, and there is breezes around the pits. Right? And the agent will model the knowledge of the world using some facts. And now if we move from propositional logic to predicate logic, then I'll be able to use a predicate, let's say B for breeze. And the arguments of the predicate are going to be, well, in this case, the coordinates of the squares. Okay, I guess I didn't really gain a lot with transitioning from propositional logic to first order logic. But if I talk about the knowledge, the rules, right, look at this rule here, which formulates what it means if the breeze is perceived by the agent. Now this is actually more powerful than what I had with propositional logic, since this one rule here covers all the cases, regardless of what square I'm talking about. Because I'm using variables here, x and y, for the coordinates, and then I am manipulating these variables to essentially express where the pit might be. This is unlike what I had with propositional logic, where I would need to have one separate rule for each square, right? So in this case, first order logic allowed me to conflate a number of rules into a single rule. So you see there in these two examples, why it might make sense to use predicate logic or first order logic. In the second example, it's because it allows me to express more succinctly the knowledge of my problem. and in the previous example, simply because I wasn't even able to express anything, let alone do some inference. Okay, so obviously the first order logic makes sense because it's more expressive, right? And that's exactly the idea. In propositional logic, there exists only facts that are either true or false, whereas in first order logic, there are objects and there is relations between objects. So you see, there is a difference in terms of ontological commitments. You remember we talked about ontological commitments at the beginning. The ontological commitments of first order logic are more complex because we assume that there is objects and there is relations. In terms of epistemological commitments, by the way, both logics are actually on the same level, since both assume that we either know something completely or we don't. Okay. Relations can be n-ary, which means they can take n arguments. If they take no arguments at all, if their arity is 0, then essentially they are the same as propositional variables. This means that our logic in this case, if we were to only use relations of 0 arity, would degenerate to propositional logic. But more often we'll have relations with arguments, and these can be unary relations that are taking just only a single argument, like student John, typically express properties. John is a student. Or we would want to use binary relations to model relations between two objects. For example, John loves Mary. So typically we would use binary relations to model transitive verbs, for example. Or we can go beyond binary. We can use ternary relations to model like ditransitive verbs, like gives John, gives Mary, gives flowers to Mary, for example. Now, obviously, because we can always use relations without any arguments, this essentially means that the first order logic subsumes propositional logic. Now, all fine. This seems to be quite good. We can express more things now, but keep in mind that this comes at a price, at a cost, and the cost is limited probability, or in other words, decidability is the thing that we lose. So there's going to be things that we cannot prove, though we can express in first order logic. I'll talk about it a bit later. Okay, now let's introduce the formal system of first order logic, and same as with any other formal logic system, we have to explain, introduce, and define the three components: the syntax of the logic, the semantics, and the proof theory. Now, proof theory we leave for next week, since proof theory is about doing inference, and inference we need for doing automated reasoning, and that's the topic of next week's lecture. But today we'll focus on the syntax first and semantics second. So syntax. Again, we start with symbols. What is the alphabet of the language? Now, since first order logic is more complex than propositional logic, the syntax will be expectedly more complex as well. We'll start with introducing constants. Constants are strings, digits, lowercase letters, and we'll use the strings here, numbers, and lowercase letters from the beginning of the alphabet to denote constants. We'll also have variables. Variables will be typeset as lower set letters from the end of the alphabet. Sometimes we'll have the need for functional symbols. These will be denoted with lowercase letters F, G, and H, for example, and then followed by parentheses of function application, like F applied to a variable X, for example. And finally, we'll have predicate symbols. Predicate symbols will be written with uppercase letters, either single letters or strings. Again, followed by parentheses that accept some arguments. Okay, now this is the alphabet. Now let's talk about terms and atoms. Term is something we didn't have in propositional logic. A term is defined recursively. A term is something that a predicate is applied to intuitively. It can be a constant. So a constant is a term. A variable is a term. And if f is a functional symbol that takes n arguments as input, and if t1 through tn are the terms, then we can apply function f to these terms, and this gives us f, open parenthesis, a sequence of terms, close parenthesis, and that's a term as well. And finally, nothing else is a term. So a term can be either a constant, a variable, or a function application. Okay, so for example, 2 as a constant and 3 as a constant are terms. Add 3, 4 as a function symbol applied to two constants is a term as well. Or add applied to a variable, which is a term, and applied to another term, which is a function application consisting of a function symbol applied to two constants is a term as well. So as you see, terms can be nested. Okay, so much for the terms. Then there's atoms. Atom is when we apply a predicate to a sequence of terms. So if P is a predicate symbol taking n arguments as input, and if T1 through Tn are terms, then P applied to these terms, sequenced and enclosed in parentheses, is an atom, and nothing else is an atom. Okay, in other words, an atom is a predicate that takes some terms as input, and terms can be constants, variables, or function terms applied to other terms. For example, loves John Mary is a atom applied to two constants, and greater than GT, for example, is an atom applied to a function application, which in turn is applied to two constants, and constants and another constant. Okay. Now that we have defined the building blocks of language, the symbols, the terms, and the atoms, we next define the rules for building formulas, and the rules are defining the well-formed formula of first order logic. But before we do so, there is one more thing we need to introduce, and these are the quantifiers. Quantifiers deal with defining the range of the variables, and we'll use two additional symbols here for the quantifiers. This one pronounced for all, and this one pronounced exists. These are the universal and the existential quantifier respectively. For what these mean, actually, I guess you can all already guess, and I think at least you knew this from before. What these mean can be guessed from how we pronounce them, but what they mean exactly formally is still to be defined in the semantics part of the formal system, and we'll talk about it in a moment. Okay, then for each of these quantifiers, we'll define the so-called quantifier scope, which is the formula to which the quantifier refers to, and it's going to be the shortest subformula that appears to the right of the quantifier. For example, in this formula, for all x, or for each x exists y, pxy, the scope for all x is the subformula to the right, which is exists y, pxy. And the quantifiers also give rise to two properties of variables. A variable can be bounded. A bounded variable is any variable that occurs within a scope of a quantifier that refers to that very same variable. For example, x here is bounded since it's within the scope for all x, and y is bounded since it's within the scope of exists y. Whereas a free variable would be any variable that occurs not bound somewhere in the formula. Okay, and now we can define the grammar. The grammar defines what it means for a formula to be syntactically well-formed formula, WFF. A well-formed formula, WFF, of first-order logic, is defined in terms of grammar rules. There is 5. The first one is an atom is a formula. The second one is if f is a formula, then not f is a formula as well. And the third one is if f and g are formulas, then so are the conjunction, disjunction, implication, equivalence. Now, the first three rules are the same as what we had with propositional logic. But rule number 4 is different as it deals with quantifiers. If f is a formula that contains a variable x that is not bound, then I can build formulas for all x, f, and exists x, f, and both of these will be formulas, WFFs as well. And nothing else is a formula. Now notice here, and that's maybe the interesting part, is these two constraints, contains and not bound. Now what this means is that a formula has to contain a variable before it can be bounded. And it has to be not bounded from in the formula already. Now this prevents me, the first condition prevents me from introducing a quantifier for a variable that does not exist in the formula, whereas the second condition prevents me from bounding a formula many times over, right? Okay, and same as with propositional logic, we'll introduce some simplifying conventions to make formulas more readable. More precisely, we'll be dropping parentheses in rule number 2, these here, we don't really need them. And we'll be dropping parentheses in rule number 3, these here introduced by binary operators, if these parentheses are the outermost parentheses of the formula. And finally, in rule number 4, we'll be dropping these parentheses around quantifiers. They don't really contribute to anything. Okay. Let's just see if this made any sense. There is 5 formulas here, and the question is, are there WFFs or not? Now, if you look at the first one here, just at first glance, it seems to be okay-ish, but it's actually not a well-formed formula. The reason being that these parentheses here, you never can actually get them using the grammar we just introduced. So, you know, keep in mind that if the question of whether a formula is well-formed or not is a very formal one. It's not about, well, you being able to read the formula or maybe understand what the intended meaning is. I mean, the meaning is anyways not something that syntax deals with. But it's about you applying the very formal rules of the grammar and trying to see if you can parse essentially the formula or if you can build the formula using these rules. And there's no way you can use the rules that we just introduced to introduce these extra parentheses around the atom here, right? So yeah, the first formula is not well formed. What about the second one? Well, the second one's okay. You can, you know, this is an atom, which is a formula, and then X is actually occurring here. You can quantify it and you'll get this formula. And Y is occurring here. You can quantify it as well. You get this formula. Maybe what might be bothering you is the Z is left as a free variable, so it's not within the scope of any of the quantifiers. I mean, there is no quantifiers for Z, but that's perfectly fine as far as syntax is concerned. Syntax does allow you to build formulas with free variables. Okay, it's going to be problematic for semantics, as we're gonna see. But you know, this is an interesting thing here that actually, you know, syntax allows you to build something that semantics later cannot work with. So it seems that the interface between syntax and semantics in first order logics is actually not the best. Okay, but at any rate, 2 is well-formed formula. What about formula number 3? Again, a well-formed formula. You know, you can start building this formula by going on from this atom, introducing the quantifier here, dropping the parentheses around the quantifier. Then you build this formula, and then you build the joint formula by introducing the implication. So yes, this is a well-formed formula. What about the fourth one? Now, yeah, the fourth one is actually not well-formed, since the variable x here is bound by and within the scope of this quantifier, but also it's bound by this quantifier. So x here is double bound, which cannot actually happen if you be following the rules of grammar. once you build this formula, there is no way you can introduce this quantifier again, since x is already quantified, is not free in the formula, right? Okay, so not a well-formed formula. And finally, the fifth formula here. Well, the fifth formula actually looks okay. It's a well-formed formula. We have z here, and the scope of all z is just this formula here, and we have x and y universally quantified, and they cover and have this y and this x within their scope. So while this is a well-formed formula, we again have a case of the z variable here being free, right? So it's not within the scope of any of the quantifiers. This z is, but this other one isn't. And yeah, again, a case where we have a formula that is syntactically valid, but contains a free variable, and this is going to be a problem for semantics later on. So to conclude, this wasn't syntactically valid, and this wasn't syntactically valid, whereas the other three are okay. Good. So much about semantics. Now it's time for the more interesting part. So much about syntax. Now it's part for the more interesting part, which is semantics. Semantics is much more interesting than syntax, especially when it comes to first order logic. So let's look at semantics. And same as with propositional logic, we'll start with the concept of an interpretation. Recall from propositional logic that an interpretation was defined as a function that assigns truth values to the individual atoms or variables occurring in the formula. And we said there is 2 to the power of n possible interpretations. Now with predicate logic or first order logic, things are different. And an interpretation is a more complex structure. It consists of 4 components. And let me go through these components here. An interpretation of a well-formed formula. Again, a formula has to be well-formed. Otherwise, if the syntax is not right, it doesn't make sense to talk about semantics. Same as with propositional logic. So an interpretation of a well-formed formula will consist of, first, a non-empty domain, D. Now, domain is actually the things we are talking about. Okay, so if we are talking about students and lectures, then students and lectures are going to be objects of the domain. Then the next component is a mapping that maps from syntax to that domain, and it maps from constants to each element of the domain. So you can think of this as a label. Each of your elements in the domain has a name, and the name is the label, and the constant is actually the name, right? So you have this link from your textual representation to pointing to an element in D. Now, so if this is your domain here, and there is different things here, and maybe one of them here is a student called John, then John as a constant, as a string here, putting this into quotation marks, is actually your constant for this particular element in D. And you need to have this mapping, right, that maps, links these two things together. Okay, so it's going to be a function. This mapping is going to be a function. Okay. Then the third component of my interpretation is going to define the semantics of functions. A function in first order logic, for example, f, x, y, is giving me some z. And the way this works is you need to define what are all the possible input combinations here and what they map to in terms of the output. And the input, each of these arguments, is actually one of these elements, from your set D. And the output, the z here, is also an element from D. So essentially your function is mapping from D to the power of n, which is a Cartesian product of the elements from your domain, basically a combination of your inputs, to a single element from a domain. Okay, so you see this is basically, you have a function here, a function symbol f, but what it actually means, you need to associate with this functional symbol f a function that maps, takes some elements from your domain and maps to another element in your domain. Okay? And finally, the fourth component is defining the truth value of the predicates. So we need a mapping from each predicate with n arguments to a truth value, which will be either true or false. So for example, if I have p, x, y, then I need a function that tells me for all possible combinations of x and y values, this is d to the power of n, where x and y are elements from my domain, which of these combinations are true, which of these evaluate p to true, and which of these evaluate p to false. Now, those combinations which evaluate the predicate to true are called an extension of the predicate. So you can think of an extension as all combinations of elements from your domain that make your predicate true, sort of all the combinations that your predicate extends over and makes them true. Okay, so you can see here that the interpretation structure is actually a lot more complex than what we had with propositional logic, where the interpretation was simply a function assigning truth values to each of the n propositional variables in my formula. Okay. Oh, yeah. There is two notes that I need to make here. First is, yeah. No, okay. We'll come to the notes. Now let's talk about the evaluation. So we have the interpretation now, and same as with propositional logic, we'd like to evaluate the truth value of a function of a formula. A formula can be either true or false. In that sense, nothing changed with our transition from propositional to first order logic. It can still be only true or false since the epistemological commitments are the same. Okay, so how do we evaluate the truth value of a formula? Again, keep in mind, same as with propositional logic, this question only makes sense if I give you the formula and an interpretation, since the formula will be true or false with respect to a concrete interpretation. Okay, so given an interpretation, we can evaluate the truth value of a formula. Again, doing a recursive computation in a similar fashion as what we had with propositional logic. Now, if we have an atom in front of us, and the atom is applied to some terms here, then we'll be evaluating the truth value by simply applying the mapping for constants and for functions. For whatever terms you have here, you'll map them with these functions from your interpretation. You'll map them to elements of your domain, D. And once you have done this, then this here will be a sequence of elements from your domain, a particular combination, and then you check the extension of the predicate from your interpretation to see if this particular combination, sequence of elements from the domain, make your predicate f true or false, right? Okay. Now, if your formula is more complex and it contains negations, conjunctions, disjunctions, implications, or equivalences, then you will basically decompose it and evaluate the individual formulas and then combine the truth value by using the truth tables in the same way as we've done it for the propositional logic. So nothing has changed here. The semantics of the operators, binary operators and the unary negation operator is the same. And finally, if we stumble upon a universally quantified variable standing in front of a formula, then we need to evaluate formula f for every element in D, and if it turns out to be true for every element in D, then this formula for all xf is true as well. Okay? And finally, let me clear this up a bit. And finally, if we stumble upon a formula that is quantified with an existential quantifier, then we need to find at least one element in D that will make the formula true. And if we are able to find it, then this formula exists X, F is true as well. We need to find at least one. There can be more than one. Okay, this is how it works. And there is two limitations here. First is that we cannot and absolutely cannot evaluate formulas that are not well formed syntactically. Okay, so your first check when somebody asks you to evaluate a formula given an interpretation is to check if the formula is well formed. If it's not the case, you can't do semantics. And then the other condition here is that formulas that contain free variables cannot be evaluated. Since for these formulas, we don't know which of these two cases applies. Is it a universally quantified variable or is it an existentially quantified one? There is no other possibility. So if the variable is not quantified, you can't really do much with it, and you have to refrain from doing any semantics. Okay, so the second thing you need to do is to check if the formula contains any free variables. As I said, unfortunately, the syntax-semantic interface is not well aligned in first-order logic, and it can happen that you get a formula that is syntactically valid, but nonetheless contains a free variable. Okay, let's look at two examples here of formula evaluation. So we are given a formula here, and I'm asking you to tell me if it's true or false. Now, again, first thing is the question doesn't make sense without an interpretation. Okay, I have to give you an interpretation, and then you can evaluate the formula. So, okay, I'm giving you an interpretation, and the interpretation contains of, you remember the four things: the domain, the mapping of constant, the mapping of constants, the mapping of functions, and the mapping of the predicates, or predicate extensions. But I need not give you all four. If there is no functions, if there is no functions or no constants, then I don't need to give these components to you. I need to give you the domain. So the domain is 1 and 2. Okay, and that's all I need to give you. In addition, of course, to the extension of the predicate, or I need to tell you for what combination of x's and y's here from the domain, and domain can be either 1 and 2, the predicate is true and for which it is false. So essentially here I'm telling you that 1 is making the predicate true, 2 is making the predicate false, true as well, and the other two here combinations are making the predicate false. Okay, now that we know this, let's go back to the original question here. What is the truth value of this formula? For all x exists y such that pxy. Now, the evaluation proceeds as follows. You're going from the outside, toward the inside. The first thing you stumble upon is for all x, right? So for all x means that, oh God, what's this? Just a second. So for all x means that you need to evaluate the formula for all values in your domain. Luckily, there is only 2. So if x is 1, that's one option. We need to consider, and x is 2, that's another option we need to continue to consider. Okay, now if you look at the inner formula here, if x is 1, then there is that exists here, which essentially says try to find one y that will make the formula true. And for y, there is two options, right? Again, it's 1 and 2, same as with x. It's 1 and it's 2. And for x, there is also x2. There is the option y equals 1 and the option y equals 2. Now, if we are here, is this formula actually true? So the question is P11 true? And it turns out to be true. Okay, now, and that's all I need, since this was an existentially quantified variable. So I'm actually this branch is done. Okay, so yeah, there is x equals 1. There is one y, this one y equals 1. that makes the formula true. Okay, but this needs to hold for both values of x, since x is universally quantified. So let's look at the right-hand side branch here, and we need to find a combination that will make the predicate true. So if y equals 1, is the predicate true? In other words, is 2, 1 making the predicate true? Well, it's not, as you can see. But 2, 2, well, this other branch is actually making the predicate true. So yeah, here. So again, we've been able to make the predicate true with x equals 2. So I conclude here that, for x equals 1, the predicate is true. There is the subformula here is true. For x equals 2, the subformula is true as well. So for all x's, and there is only 2 in my domain here, the formula is true. That's it. This formula here, the entire formula is true. Okay. Let's look at another example. In this example, we are given an interpretation, and we are given 5 formulas, and we need to evaluate if the formulas are true or false in this particular interpretation. Now, the interpretation is actually quite simple again, contains a domain with only 2 elements, and there's going to be a predicate symbol P, and this is its extension, which essentially means for these 2 combinations of this obviously binary predicate, the predicate is true, otherwise it's false, right? And now we need to evaluate the truth value of the following WFFs, which means the formulas here are allegedly syntactically valid. Okay, that should be the case. Otherwise, it doesn't make sense to evaluate the formulas. Okay, so let's look at the first one. Exists x for all y's such that pxy. Again, you can do this, step by step, but I'll try to do this a bit faster this time around. So what I'm after here, I need some x that will make this formula true, and this formula needs to work for each, make the predicate true for every y. So if I take x to be a, then this basically means I should have b, PAA and PAB. That doesn't work because PAB is not in the extension of P. If I take x to be b, then again I would need to have PBA and PBB. Well, PBB is okay, but PBA is not covered by the extension of P. So I conclude from this that the formula 1 is not true. Okay, so it's false. Let's look at the second formula here. Exists y such that not PAY is true. Again, let's try with y being a. Okay, so if y is a, then I would have not PAA, but not PAA is covered. PAA is true because it's in the extension of P, and therefore not PAA is false. But if I take y to be b, then I would have not PAB, and this is true since PAB is not in the extension of the predicate, right? So yeah, there is a possibility for me to pick a y such that the subformula is true, and therefore the entire formula is true. Let's look at example number 3. For all x, for all y, pxy. This basically means that all combinations of a and b should be covered by the extension of the predicate, but this is obviously not the case since ab and ba are not covered. So this formula number 3, is false. Let's look at 4. There exists x such that not pxy. Okay, if I set x to a, then I'll have not pxy something. Okay, now the problem here is the y here. The y is a free variable. It is not quantified, and I don't know what to do with it. So formula number 4 is syntactically valid, okay, but you can't really evaluate it since you have a variable here that is free. Okay, so 4, there is no answer for 4. You can't evaluate the formula. What about the fifth formula, an implication here? Now, whenever you have implications, things get a bit more interesting. For all x, for all y, if pxy, then pyx. Before we actually solve that one, notice that what the formula is saying is that the p, if considered as a binary relation, is symmetric, right? So if pxy, then pyx has to be true as well. And it should be the case, since, yeah, let's see, okay. For all x, for all y, is essentially telling us that we need to go through all 4 combinations here. Why is it 4? Because we have a and b, right? This is 4 combinations of the domain elements. Don't confuse this with interpretations. I'm not saying that this is 4 interpretations. Because we are dealing here with a single interpretation all the time. It's the interpretation given by the domain and the extension of the predicate. I'm now about the four pairs of elements from D. Okay, so if AA, what do we have? What do we have then? We have PAA implying PAA again. Okay. Will this be the case? Well, PAA is true, right? Because it's covered by the extension. And if this is true, then this is true as well. And true implies true is true. Okay, so this is okay. This is true. The other option is PAB, say, and this should imply PBA according to my formula. Well, is this true? Well, it's not true. Okay, if the antecedent is not true of an implication, then the entire implication is true regardless of the consequent. And we can go on. PBA implies PAB. Again, same case here. The antecedent is false, therefore the entire implication is true. And finally, PBB implies PBB is true, right? Since the antecedent is true, as it is covered by the extension of the predicate, and the consequent is true as well. So true implies true is true, and we get true as well. So, for all 4 combinations of A and B values from the domain, and this is what was required by the 2 quantifiers here, the sub-formula here is true, so the entire formula 5 here is true as well. Okay. And same as we had with the propositional logic, there is a bunch of equivalences that hold in first order logic. I will not go through all of them, and it doesn't really make sense to learn these by heart, but I'll just highlight a couple of them which we'll be using frequently. The 2 quite important ones are these here. Not exists, not for all x, fx, where the angle brackets here denote a formula that contains x. So I'm basically saying it's not the case that for all x, some fx. Now this is the same as saying there exists an x such that it's not fx, right? And then similarly, it's not the case that there exists an x, fx is the same as saying for all x's, it's not the case fx. If you think about them and come up with examples from everyday language, you'll see that these actually make sense. Now, technically, what this amounts to is when I have a negation operator in front of a quantifier, I can jump with the negation operator over the quantifier, and when I do this, I'll flip the quantifier. Okay, so for all, not for all gives me exists not, and similarly, not exists will give me for all not. Okay. And there is more of these equivalences, but we'll come back to these when we actually need them for automated reasoning next week. And lastly, in this part, I'd like to emphasize I think I already mentioned, and that there was a price to pay for increasing the expressivity of logic. So first order logic can do things, it can express things that the propositional logic cannot, but the price that we had to pay was that we lose decidability. Before actually explaining what this means, let me first know that the first order logic concepts of validity, inconsistency, and satisfiability are defined just in the same manner as for propositional logic. Now the difference though here is that the interpretations are different, right? The propositional logic formula with n variables has 2 to the power of n interpretations. Why is this? Well, because there is 2 to the power of n possible assignment of truth values, binary truth values, true and false, to n variables. And that's exactly the number of rows that we are going to have in a truth table. Now, this is different when it comes to first order logic. How many interpretations have we got for a formula of first order logic? Now, the notion of variables is different. It doesn't really make sense to say it's 2 to the power of n variables, since the variables here are actually ranging over domain elements. And you have to think about interpretations, right? So in propositional logic, an interpretation was an assignment of true and false values to variables, and it made sense that there is 2 to the power of n of possible assignments. But the interpretation in first order logic is defined differently. An interpretation, recall, is a structure with 4 elements: the domain of elements, the mapping for functions, the mapping for constants, and the extension of the predicate, right? So the question here is, how many different interpretations can we come up with? And the truth is, well, you can come up with infinitely many. There is no limit really to what any kinds of interpretations you can define. You can always come up with infinitely many possible domains. That's the thing, and yeah, while the number of mappings within these domains gonna be limited, the number of domains will not, and moreover, some of these domains will be infinite as well. So you see, the problem then is that there is no way we can construct truth tables in first order logic, because an interpretation is not a row in a formula. An interpretation is so much more, and there is infinitely many of them. How does this affect the semantics? Well, it does. Think of the logical consequence. The whole idea of proving logical consequence was that we are able to check if whatever interpretation makes the formulas true, the premises true, is also making true the consequence, right? And we've done this by explicitly enumerating all the interpretations and then checking if this is the case. Now, there is no way we can do this for first order logic because we cannot explicitly enumerate an infinitely many interpretations. So the consequence for semantics is that we will not be able to do the usual business of proving validity, inconsistency, satisfiability, and logical consequence in first order logic. So yeah, we can't prove logical consequences because we can't do an exhaustive enumeration of all the interpretations, as there's infinitely many of them. And that's the root of undecidability of first order logic. Now, is all hope lost? Well, it's not. Because enumeration of all the interpretations does not work, we'll have to look elsewhere for a solution on how to prove things, how to do inference in logic. And the mechanism for doing so comes from the third component of the logical system, which is the proof theory. And we'll talk about proof theory next week. So proof theory will allow us to sidestep the limitation of semantics and logical consequence in a way, and allow us to prove things without really resorting to enumerating all the possible interpretations. But keep in mind that regardless of what method we use, the method is going to be limited by undecidability of logic. It's a property we cannot really avoid. Okay, and this now brings us to the topic of mapping natural language sentences to first order logic formulas.